Again, welcome everyone. Today's session is about introduction to world models. I think it's another big name in AI right now. And specifically, we are also looking into the paper and also the model, the world model from Meta. We are looking deep into what is the model architecture, what are the major findings and the results, and what are the future work. So first, actually, I want to start with introducing what is the world model. Intuitively, actually, every human being has a world model, right? So, for example, if I play this, you know what is a possible physical event and what is impossible, right? So if you watch the ball like rolling down the slope, well, again, and then you know the ball is going to flying out over here. But if you see the ball passing through the slope and bumped, and then it's still sliding down the slope, you know it's impossible. So this is some inherent model that already exists in our brain that we can easily tell what is a possible physical event and what is impossible. I like to play a video from Yan Nakun. Let's hear about what he says.
AI is a technological challenge as well as a scientific challenge because we don't know how to build truly intelligent systems yet. It's one of the big scientific questions of our time. What's the universe made of? What is life all about? How does the brain work? Or what is intelligence really? Hi everyone, my name is Yann Lequin. I'm the chief AI scientist at Meta. As humans, we think that language is very important for intelligence. But in fact, it's not the case. Imagine a cube floating in the air in front of you, and imagine rotating that cube by 90 degrees. You can sort of picture this in your mind, and this has nothing to do with language. Humans and animals navigate the world by building mental models of reality. What if AI could develop this kind of common sense, an ability to make predictions of what's going to happen in some sort of abstract representation space? We call this concept a world model. Allowing machines to understand the physical world is very different from allowing to understand language. A world model is like an abstract digital twin of reality that an AI can reference to understand the world and predict consequences of its action, and therefore it would be able to plan a course of action to accomplish a given task. It does not need millions of trials to learn something new because the world model provides a fundamental understanding of how the world works. The impact of AI that can reason and plan using world models would be vast. Imagine assistive technology that helps people with visual impairment. AI agents in mixed reality could provide guidance through complex tasks, making education more personalized. Imagine an AI coding agent that can actually understand how a new line of code will change the state of the variable of the program, the effect on the external world in the context of existing code. And of course, world models are essential for autonomous systems like self-driving cars and robots. In fact, we believe world models will usher a new era for robotics, enabling real-world AI agents to help with chores and physical tasks without needing astronomical amounts of robotic training data. This is a very exciting time for AI research and a captivating set of scientific questions in front of us. We want to understand intelligence itself, as well as learning, reasoning, understanding the physical world, so we can build systems that can help billions in their daily lives. We're excited to announce the release of V-JEPA version 2, the next step in this journey. Stay with us as we continue exploring the possibilities of world models and push the boundaries of AI research.
Okay, so I think Yan Nakun, I think he already explains what is the world model well. It's all about understanding the physical reality and also anticipate the outcomes and plan and able to plan and reason about, okay, what are the action to take? What are the most efficient strategies to use, right? And this is kind of like some drawings about what is happening in our brain. So we humans is actually such an agent, right? So we in our brain we also have a world model. Whatever action we are going to take, we also kind of have some expectation about what is the expected outcome, what is the goal that we want to achieve, and according to the goal, we are also going to plan, say, how to learn about the AI, attend meetups, networking with others, then this is a course to take. So actually we make the strategies and we take actions in order to reach the goal. If you look at the development of the world models, in the beginning, it's actually using reinforcement learning. So because the reinforcement learning requires the agents to interact with the environment, right? Able to take action and get feedbacks from the environment. So if we can simulate the environment, that will facilitate the training of the reinforcement learning. So this gives the kind of the birth to the Dreamer V3 model released in 2023. So this algorithm uses the internal world model to train the agents, kind of using the simulated dreams, so that the agent can, do lots of iterations and training just with the dreams there in the world model. And it actually show very effective results of using the world model to train the IL agent. And then in 2024, the World Labs, I think is again founded by the Stanford professor, Fei Li. And she's leading the effort to build large world models and able to enable this spatial intelligence there. And then I will also share some example later that you will see that how they're able to generate a 3D world just from a 2D image. And then in 2025, you see like a lot of world models are actually released and it's like under rapid development, like from NVIDIA on the Cosmos, right? It's mainly proposed or designed for robots and auto drive. And then the Meta released this the V-JEPA 2. It's also the main purpose of this is also to allow the zero-shot robot planning so that the robot can figure out like just based on the initial state and then the end goal state is able to perform the actions without a specific training. And then in August, Google also released the Genie 3 model. It's again an interactive world model and provide these 3D environments like from text or images. And actually just yesterday, I just found out that Meta released another one called a vision language world model. So this is kind of another improvement over the JEPA 2. It's trained for language-based world modeling, while this JEPA 2 is based on video and images. Well, this one also evolved to kind of use languages to observe and predict the world evolutions. Okay, and then I will show a few examples. So this is one example about, say, if we have a world model, we can actually simulate, right? Like what a 3D world looks like. And say you put a very unrealistic, well, a little bit realistic, but it's kind of like a dream, right? Like a picture. And then using the physical world model, you can kind of imagine what is the 3D world. And then you can actually do the active explorations about like moving up and down, and then you can see the surroundings and looking from different angle what the image will looks like. Powered by a world model engine. So this is also from the Google recent release. This is again like not from image to 3D world, but from text to 3D world. So this is the prompt, like from a glacier, lake, branching paths in the forest, and flowing mountain streams, right? And then it's able to generate a high quality kind of like a 3D. Again, you can do the exploration yourself, like moving up and down, left and right, to observe the environment there. And with the world model, basically what you see actually kind of follow the physical rule, kind of try to follow the physical rules so that you do not see something like unrealistic from that. Yeah. So I see lots of examples on this about how the world model is able to basically help simulate the environment and allow human to do these 3D explorations. A big application also is on robotics, more specifically focusing on zero-shot robotic planning. So what is zero shot? Zero shot means like you don't give any training labels, right? So usually in order to train a machine to perform some tasks, you need to connect lots of inputs and outputs so that the machine learns how to perform the task. But the zero shot is you actually trying to create a generalized model so that in unseen or unfamiliar environment, the robot can learn or figure out the strategies and actions to take in order to achieve the task. So in terms of the robots, I think there's also lots of applications. For example, one of this is a packing robot, like packaging, right? Like putting this in a package. It may in any environment, and you're trying to do say grasp, pick and place, all of that. So how can we enable a robot to do any pick and place to anywhere, and all the motor actions are actually figured out by themselves. Another thing I want to point out is actually I want to compare it to the large language models because I think the boom of AI is actually driven by the large language model, right? And then if you compare the world model to large language models, as it tells, is focused on languages, right? So all the knowledge, the reasoning tokens are in languages, while the world model is more focusing on the sensory data, such as the images, videos, environment simulations. And right now I see that the world model is also trying to use the languages as well in it to be a more kind of a universal model. And in terms of the architecture, actually, I do not see a huge difference in terms of like what model architecture they are using. So I think they're all using transformers majority. And of course, like world models were more focusing on using the encoding the encoder part in the transformers to learn latent representations of the world. And then the objective, yeah, so large language model is like kind of next token, next word prediction, right? And then the word model first is to predict the environment state. So this is latent representations of the surroundings environment. And also it can also take in an action, right? Like say if there are say 10 actions to take, and by taking one action, it can automatically predict what is going to happen. So there will be some encoder state and also some prediction stage. We will see later in JEPA model. In the training paradigm, I think they are all using the self-supervised learning. So self-supervised learning is like basically it's trained on a large corpus of unlabeled data, right? Think about the large language model. The pre-training is just using like always predicting the next token. You don't need to provide any additional labels in the pre-training stage. Same is the worldwide models. The world models is also doing the self pre-training on the say videos, right? And the images to figure out to understand the state here is actually that video frame or images that is trying to perceive. In terms of the applications, LM will focus on the NLP task, and world models is more on the physical related tasks, such as simulations, robotics, and also, as I mentioned, like it can be also used in the model-based reinforcement learning as a simulated environment to train the IL agent. And the grounding, in terms of the grounding, is more like a statistical and linguistic for language models, and word models is more trying to figure out the causal relationship, the physical rules, and which is very natural for human being, right? To understand like what the physics, basically just observe and learn the physics that happening around us. Cool. So basically this is kind of the comparisons with LM.
Meta just dropped V-JEPA 2, a revolutionary AI world model that thinks like humans before acting. This 1.2 billion parameter beast can predict physics, plan robot movements, and understand cause and effect in videos without any human training. trained on over 1 million hours of video, it achieves 65 to 80% success rates in zero-shot robot control, meaning it can control robots it's never seen before in completely new environments. But here's the crazy part. While humans score 85-95% on physical reasoning tests, even V-JEPA 2 struggles at chance level, showing we still have a massive gap to bridge. Meta's also releasing 3 new benchmarks, including IntFiz2 and Causal VQA, to help researchers build better AI that truly understands our physical world. This could be the breakthrough that finally gives AI systems the intuitive physics understanding that even toddlers possess. Drop your thoughts in the comments. And don't forget to like, share, and subscribe to @TheNeuralAI for more cutting-edge AI innovations.
And then if you look at what is the overall framework of JEPA model, it actually has 2 phases. So one is the pre-training phases, and then the post-training part. So post-training is more to ground the pre-trained model into different application scenarios, such as Q&As against videos, or doing the classification and object detection. You can also do so this is mainly developed for robotics, right, to do the action conditioned predictions. So, and during the pre-training phase, you see that it's actually pre-trained on a large video and images. And then during the post-training phase, so it will has more like a supervised data set. For example, for the robotics data, it actually also use the states, which is actually an image of the position of the robots, plus the actions such as the motor, right, like move left and right and by how much, and to predict the next state. So this is how they are kind of what data set they're using and how they conditioned on the robot actions. If I compare this pre-training to the previous model, kind of like model training, I think the key difference is right now the JEPA model, the one model predictions are more focusing on semantic features instead of the pixels, right? It actually still use a very similar approach. For example, doing the mask. I think we keep using the mask, right? Like randomly mask out some sub-regions of a video frame or images, and then ask the model to predict, to recover it back, and trying to minimize the errors between the recovered patches to the regional ones. But the difference here is instead of directly kind of calculating the errors between the recovered versus the regional one in pixels, they compute the loss based on the latent representations. The latent representation, you can think of it as just a vector representations of the content. Right? So there will be a video encoder, say the input is a video. So there will be a video encoders over here. And then after that, it's going to directly predict what is the representation, output out of the encoder. So in the end, it's still a vector. Instead of pixels, it's still a latent representation of the missed patches. And then it's just going to compare the loss function between the latent representation, which is a vector of the mask tokens versus the original ones after the encoders. So the second phase is the post-training, right? So the post-training here is still the same, where you still have the encoder to transform the content into a vectors. And then you add over here will be the actions, right? So you use all the previous time steps, the frames, to predict the next time step. Say after the robot taking this action, then the position of the arm will change, right? And then it's going to predict, after taking this action, what the state will look like. Basically, is this next frame, what the next frame will look like. If you look deep into the pre-training part, actually they are using just a vision transformer If you are interested about what is a vision transformer, I did give a past meetup on vision transformer, VIT. So you can check out our past recordings on VIT. So both the encoder and predictor part are using the VIT. And then they also use positional embedding, and more specifically like a 3D one, because it's like a 3D data, right? Because for videos you have the X, Y, and also you have the time step. So it's more like a 3D data. So they use a 3D rope to encode the positions of the information. And then the loss again is the mask prediction loss. So mask prediction loss, yeah, you don't need to. P basically stands for the predictor, right? So you can just think about it. Okay, this is the representation prediction of the masked video, and then this is the output of the original video without any masking. And then it's trying to minimize the difference between the prediction and the original. And again, this loss is calculated in the latent space, right? So it's in the representation, which is the output of the encoder, rather than at the pixel level. So that's the kind of, you see, like from the model architecture perspective, there isn't much difference in terms of what is the architecture or the training procedure. But the key difference first is the objective, right? So objective is on the difference between the latent vectors, and also the changes, kind of the innovation they have made about how to train this, including that EMA trick, and also the stop gradient, like other training procedure they have modified to stabilize the training. And then in the paper, they also mention about like how they scale up this model and to see the improvement in the performance. So there are many 4 dimensions, right? So first is a data dimension, like they increase the pre-training data size from 2 million to 22 million, like 10 more, 10 size. And then model scaling, so basically we have an encoder here, right? The encoder architecture from the 300 million to over 1 billion parameters. Yeah, actually the biggest model right now they in the paper is actually just 1 billion. And also they figure out how to do the longer training, basically to extend the number of iterations from 90 to 252,000. And then also higher resolution, how they are supporting a mixed resolution training. For example, starting with a low resolution in the beginning, in the warm-up phase, and then when they decay the learning rate, they will increase the data to higher resolutions. And then this part is the summary of how the model performance varies, right? Like how the model performance varies about like when you add data scaling, when you add model scaling, et cetera, et cetera. And you see how the basically this prediction accuracy improve over time. And I think the next key question is like what pre-training data set they use. There are many use of video mix, 22 million pre-training data sets. And this data sets is mixed, right? So it's a mixed video data sets, including the something. So it's pretty interesting name here. Something video. And this video data set is a first-person perspective video. So it's kind of like you see the video from the first-person angle. And then the kinetics is a third-person perspective. And how to 100 million, so this is a YouTube tutorial videos, and then also some other general YouTube videos. And over here, they also mention some curation process. So this is more to reduce the noisy content. So if there's like from a minor group, they are doing some like a latent representation of the video, and then they're doing some clustering of the video. So if the video is like an outlier or it's like just sits its own in the cluster, they are just removing that, such as the cartoon part or the clip part style. I don't know what is clip part style, but they're trying to do some denoising of the data sets. And then they mainly specifically apply this curation to this 1 billion data. which is also the largest, which also has the largest samples in the training data. And then you see so this is more deep dive into the data scaling effects, and also after they apply the curation, right, the data cleaning, what is the effect on the accuracy of the performance? Actually, I do not see a big jump. On average, I do not see a big jump if you pre-train with 2 million or 22 million. But it does have some effects on certain data sets, such as on I think this is from the image net, on the images data set. So it has a big difference on some data sets. And also with or without curation, some data sets is like insensitive to the curation, while some data sets is like, has a big jump. Well, it's like 2 to 3% jump for some data sets. The next is the model scaling. So they are using the vision transformer, right? So they select the VIT backbone of low, high, and G is kind of like a giant up to 1 billion, so 1,000 million parameters. And then you see the kind of, so the scaling law here will continue to see the model improves, the encoder improves. And also because they are using a progressive training, so there are two phases in the progressive training. When they pre-train with the shorter video clips in a lower resolution, and then in the cooldown phase, it's like a linear decay of the learning rate. They increase the video resolution and also increase the duration. So you will see, and actually they use this to improve the training efficiencies of these videos. So if you use if you were using a single resolution, say high resolution training from beginning to the end, you may end up with requiring more GPU training days to complete the full training. And right now, if they use this strategy to train, they actually improve by 3x in terms of the training resources. So they also mentioned about the video duration. It's still actually not a lot, right? So you're saying it's up to 64 frames. So actually it's not a very long video. And again, they also mentioned this is one limitation they want to improve to be able to be trained on longer horizons of the videos. Cool. Okay, so that's a pre-training. So the pre-training is just like pre-training in large language model is on predicting the mask tokens, but in latent space. So just remember that. That's it. And then if you want to more deeper dive, you can look at to understand more about the stop gradient, L1 loss, and why applying EMA can help stabilize the training. So that will kind of illustrate it more in depth in the paper. Cool. And then after the pre-training, this is one type of post-training. It's more focusing in the robot action prediction. So what it's trying to predict is again the previous video frame. So this is how, say, there's a robot arm is moving around and trying to pick up a cup, right? And then it's moving around. So you also have the action, kind of the motor data there about how the robot arm is moving in the space. And then you also have the state. So the state is basically just these video frames about what is the position of the robot arm in the space. And then you have your data sets as like T0, T1 up to T3. Say you use 4 frames, and then you're trying to predict the next frame. Say the next at time T, you have your robot action, right, from the motor sensor data. And that will be your input to the predictor. You also have the current, kind of the past states, basically these video frames of the robots. And then given this robot action, what will be the next video frame looks like? So this data is kind of trying to teach the model mapping from the robot action to the state. Like after taking the action, what will be the position looks like in the image. So this is what it's trying to predict. And then in the prediction, they also have 2 phases. So one is using the teacher forcing loss. because it's a kind of an auto regression way, right? Auto regression is like you use the past timestamps to predict the next timestamp. In the teacher forcing way, you always use the ground truth. So basically the encoder, the output from the encoder, which is the latent representation, as the input to the predictor, right? So over here, like for example, at t0, the end is to predict the latent representation of t equals 1. So this is z1. And then you directly use the ground truth over here of the encoder over here. So this is the direct output from the encoder from the actual video frame, and then to predict the next time step. Again, you use the actual latent representation to predict the next time step. So that's the teacher enforcing. While in the AC rollout way, you use a predicted one, right? So you, instead of using the Z1, which is the actual output from the encoder, you use a predicted output from the previous time step, right? So this prediction will go over here, which is actually trying to predict this. So instead of using the ground truth one, you use the predicted one over here. So you see, like this way, you kind of will have some propagation of errors if your time is like very long. So the error will propagate over time. So that's why, like usually in the auto regression model, there is like two kind of you can do like a two losses. One is using this teacher enforcing, and one is just using the predicted value as the input at the next time step. So in this training, they combine these two losses. It's kind of just like 0.5 multiplied by this plus a 0.5 multiplied by this. So they are trying to minimize the loss for both. Okay. So I want to make sure that what we are trying to predict and what we are trying to is clear, right? So it's always using the past video frames plus the robot action, so which is a gray area over here. So it's the actions plus the actions with the past video frames, and we want to predict what is the next video frame, right? So that's the purpose of this. And then if we have this model, how we are going to use it? This shows an example. So you have a start video frame, and this is your end goal, the ending video frame. So basically then the robot needs to figure out the actions, basically all the motor actions it's going to take in order for the position from the beginning to the end. And this is all automatically happening because you have an action prediction model. You know what the video frame will looks like if you take this motor action, right? So once you train that model, you can use that model to guide the robots to figure out what are the action to take, so that you can gradually kind of move this video frame to this ending frame over there. So the model will plan by imagining all the possible actions, and then it will pick the action it will most likely to succeed, so that they can just do the layer shot, figure out what actions to take to reach the final video frame that you are targeted at. I think it's a very interesting way to frame the problem. So it's just like the problem is framed differently from previous how we do the robot training. So this is kind of the data set they have, right? So it's more for the zero-shot robot control. And in this data, you have a start frame, and then you have your goal frame, right? And then basically you want the robots to figure out the motor actions so that the position of the robot arm can kind of getting closer and closer to the goal frame it has. And then you will see the kind of this loss, like position error. So for example, this robot is moving the arm, right? So this is the beginning, this is the end. And it's trying to move the arm so that it can match the end position. And then you will see there, for example, 5 action or 6 action it has taken at different time steps. And then the position error is kind of decreasing over time. This is another like beginning position, ending position, beginning position, ending position, and then the robot is using that action state predictor model to figure out what is the motor action to take at each time step. They also do this peak and place, right? So you have this again beginning and end. So this is your input to the model, and then the robot is using that state action predictor model to figure out, okay, what is the action to take along the way. For example, first I need to pick it up and then move it up to the table and then need to drop it down. All right. So this is how, so basically you just present the beginning frame and the ending frame, and then the robot will plan all the action in between in order to reach to the ending frame. So they also benchmark, so basically they just benchmark the success rate. So they gave it like 10 trials to the robots, and then to see like how many times that the robot is able to successfully grasp or reach or pick and place. And then it's kind of 80% of the times. Reach is easy. Reach is easiest task. And then the grasp, reach, and pick and place is around like previously, and the prior model is around like below 20%, and then this model is able to reach to around 80%. They also use the pre-trained video encoder to perform the understanding task. So the understanding task, say you have this complex gestures, right, in the video sequence, and then you want to classify it into what is the intention of the human, like what of the gesture, for example, turning the hand around, right? So this is more like you can think about it as a classification type of model to see what is the action of the human being. So these are all the methods of previously reported methods in literature or other image encoders or video encoders. And then this is the motion understanding data sets or appearance understanding data sets. So you can think about it as all as a multi-class classification problem. And then you will see what is like the pre-trained model by V-JEPA is able to get to how much higher, like 3%, like for example, so this like previous one is around like a 70, like 68%, and they is able to boost the performance in terms of the understanding of the video sequence on a brand new data set. So this is another action anticipation. So if you see a sequence of video frames, you want to predict what is the next action the human is going to take, right? So basically, there are like a set of actions, and then the model is going to predict from the highest likelihood to the lowest likelihood over there. So after 1 second, what is the action is going to take? For example, the wash the sink or put the plate, which is correct. Of course, there are failures as well, like the model fails and understanding what the human is trying to do over here. To be honest, I also don't understand. Maybe it's like trying to get the things out of the cabinet. And over here is kind of we'll put it back, put it back to the shelf there. The last one, they also benchmark against on the video Q&As. More specifically, like for example, there's a very popular benchmark for multimodal video understanding benchmarks, right? So you have your video, and then you ask a question to the video. For example, what happened after the person took the food, and then you give a multi-choice for the model to select. So this is what the data set looks like, right? So it has some action related data to predict the human actions, to predict, to detect any object, the positions, and even counting. And actually counting is a difficult task. It's not as easy as how human perform the counting. It's actually one of the most challenging tasks for the V-JEPA model. And then they compare this JEPA model to all the off-the-shelf image encoders, and then they're able to see the boost of the performance. And I would say there will be still a big gap because you see the average performance is still around like a 52% or up to 70%. So there's still a big gap to improve to kind of better encode the video, right? We need a better latent representations of the video so that we can do better Q&As to really understand the meanings, semantic meanings, and the intentions of the video. Yeah, so they also compared to the video language models like from the Quen and Palm of similar size, and they claim to be the beat the state of the art in around 8 GB model. Of course, when you scale in the model, the performance will also improve along with it. But usually when we compare the performance, we kind of fix the model size and then to see whether the performance kind of can consistently better across all the benchmarks. Yeah, so this is all what they are trying to do, and they did mention about the limitations of the work and what are the next steps, such as support for longer horizons. Right now, you see still up to like 32 or 64 frames, right? So it's like a very short video. So they are looking to extend this work to a longer horizon task or even more complicated tasks that requires a longer video durations. So this will require more further innovations in the modeling and training procedure. Also, the second is the language-based goal because this one is right? It's vision-based because this is how we understand the physical world. It's all by images and videos, so that we kind of know what is going to happen next based on the physical rules that we already aware of. And even though this is like starting with the video and images is very natural for the task, but there are also other tasks are with language goals in the digital world, right? So how can they extend this to a language-based goal? Well, the languages it's putting out will also be kind of aware of this common sense in the model. How can we distill that common sense in the model? There's also a strat on scaling up the models. So right now it's scaled up around like 1 billion parameters, and they keep seeing the model improvement. So they say like they also see some work already investing in scaling the vision encoders to as large as 20 billion parameters. If you look into the future of the world models, what I see over here in terms of the architecture, not much difference from the transformers, to be honest. But it's more about like how we frame the problem, how we train the model. And then the key part of the world model is actually to understand the physical world, able to predict. So if you take an action, right, just as a robot's training over here, if you are able to take action, you should be able to predict what is going to change in the physical world, right? The position, or posture, right? So you should be able, or the model should be able to already predict or foresee what is going to happen next. And then with this understand, using the encoder model with the predicts using the action state predictor model, then there should be a planning part. So the planning part is more like to figure out using this encoder, understand and predict. Then we can use this to better plan what are the actions to take in order to reach the final goal that either the robot or the task wants to achieve.